Today's lesson is operations with radicals. So this thing here can be read as the square root of 4 or radical 4. That's because this symbol isn't just a square root sign, it's also called a radical sign. What's under the radical is called a radicand. So that's just some vocabulary for you. Here's some properties of radicals. So we're going to go through these properties as we do the examples. Example 1, we're going to simplify each one of these. So first of all, simplifying a radical means you want to put it in lowest terms. Well, what does that mean? That means that the square root of 45, if there are two factors of 45, two numbers that multiply to 45, and one of them is a perfect square, I can pull it out. So what I mean by that is 45 is the same as writing 9 times 5. Okay, so 9 times 5. Now looking at the multiplying property here at the top, the multiplying property, I can either write numbers as I did with 9 times 5, or I can break them up like that. So I'm going to break this up and I'm going to write it as the square root of 9 times the square root of 5. So the square root of 9, of course, is 3. So that's 3 times root 5, but I don't need the multiplication sign. I'm just going to put 3 times root 5. It's going to look like this. So that is a radical in lowest terms. So it's now called a mixed radical. It's like a mixed fraction. Up here is the word mixed radicals. Mixed radicals have an integer in front and then a radical, which is irrational, beside it. So let's try that again with the next one. We're actually starting with a mixed radical. We're starting with, there's already a -3 in the front. That's fine, but I still want to do the same process with that square root of 32. Are there numbers of 32, factors of 32, and any of those numbers are perfect squares? So let's say you were thinking of 8 times 4. Okay, so 4 is a perfect square. I'll put that first. 4 times 8 is 32. So now I'm going to write it like this. I'm going to break it apart. That's 4 times square root of 8. So the square root of 4 is 2. This is equal to 2. So I'm just going to go ahead and multiply these two together, and that's going to give me a -6 root 8. But the square root of 8 is not in lowest terms. I can reduce it some more. So what are two numbers that are factors of 8? One of them is a perfect square. Well, that's 4. Remember, this is not a perfect square. A lot of people do. They do square root of 2 is 1. No, it's not. Square root of 2 is not a perfect square. So don't use that number. But 4 is 4 times 2. So again, I'm going to separate them and write it as 4 times 2 like this. And the square root of 4 is 2, so what I have there is -6 times 2, -12 root 2. Now because I had those extra steps there because actually at the beginning I didn't take out the biggest perfect square root. If I would have, out of the 32, if I would have recognized that a 16 could have come out of that right away, if I would have written instead up here, if I would have written it as 16 times 2, then I would have got -3, and the 16, when the 16 comes out, the square root of 16 would be a 4 times 2. I'm going to get the same answer. I'm going to get this -12 root 2, but I would have got it a bit faster. So it's just like reducing fractions. If you don't reduce it by the right number first, you just keep going until you get it right. Let me erase that. So the next one, the square root of 5 times the square root of 7, those numbers, neither of them can be reduced. They're both prime numbers. I can't make them mixed radicals. So what I can do is I'm going to use this multiplying property and put them together because I'm simplifying. So I'm not going to leave them like that. I'm going to simplify them and just write it as a square root of 5 under 1 bracket times 7. So the square root of 5 times 7, that's just a 35. So we simplified that by just having one radical. We only have one radical in all these answers. We have one radical in our answer. Sometimes when we multiply two numbers together, what happens is we get a new number inside that can be reduced. Can 35 be reduced? Are there any factors of 35 that are perfect square numbers? No. So that one's done. So that's simplified because we've just got it together as one radical. D. D is division. So look at the dividing properties here. I can either write them as two separate radicals or I could put them together as one. So I could write it like this, 48 over 6. So 48 over 6, of course, that's under the radical, what's 48 divided by 6? That's 8. And 8 reduces to what? What are the perfect square? What's the perfect square number that's a factor of 8? It's 4. So we take out the 4, we write it as 2. You don't have to always write this step that I'm doing right here. You can skip that when you're ready. The square root of 4 is 2, so that's 2 root 2. So that one's done. We're down to one radical, and our radical is in lowest terms. Last example on this part here is square root of 2 over 9. So right here we had 48 over 6. We reduced that to an 8, so that was helpful. But here, 2 over 9, I can't reduce that at all. So I'm actually going to do the opposite thing here. I'm going to put it back into two separate radicals. The reason I'm doing that is because I can find the square root of 9. So I could reduce the denominator at least and get the square root of 2 over 3. At the bottom it says, what should your answer look like? If the question says simplify, if your question says simplify, it means your answer should have one radical in it, right? Not two. Your answer should have one radical in it. Either it's an entire radical or a mixed radical, but your radical should be in lowest terms always. So if it says simplify, you've got to get that radical into lowest terms if you can, like we have for all of these here. Example 2, simplify. Now we know what that means. But here's a new step. We're going to collect some like radicals, same as like terms. We're not actually ready for that step yet. We're going to start going back to what we just did before. Just look at that 4 root 50. Can that root 50 be reduced to lowest terms? It can. So I'm going to write that 50 as a square root of 25 times 2. Now how about the 7 root 32? Can 32 be reduced? Yeah, we did that one before actually, and this time I'm going to go with 16 times 2 instead of going with the smaller number. Minus 5 root 7. How about square root of 7? No, that can't be reduced. We'll leave that one alone. And the square root of 98, it's a big one, but yes, that's 49 times 2. Always put the perfect square number first, and remember, this is not a perfect, we cannot take the square root of 2. Okay, back to our first row. So I don't need to always break, I will this time here to explain what I'm doing, but I don't need to keep always writing this out twice. 25 times 2. I could just go ahead and instead of putting the 25 there, I could go ahead and just put a 5 there, right? I could skip that step. I'm going to skip it here. So instead of writing out root 16 times root 2, I'm going to go ahead and take the square root of 16. So that's 7, and the square root of 16 is 4, but then I still have a square root of 2. Minus 5 root 7, minus 2, and again I'm going to skip the step. The square root of 49 is 7, and square root of 2 is 2. It's not 1. Oh, so I didn't clean this one up right away, so I have to do it now. So now I have kind of that extra line in there. 7 times 4 is 28. That's 28 root 2 minus 5 root 7 minus 14 root 2. Okay, we're getting there. We've got 20 root 2 plus 28 root 2. So we've simplified all of our radicals now. None of these radicals any longer can be reduced anymore. So now we're at that extra instruction bit here. Collect like radicals. It's the same as like terms. Let me just review the like terms with you. If I had 2x plus 7x, I would get 9x. I would not get 9x squared, right? I would just get 9x. So if I have 20 root 2's, and then I get 28 more root 2's, and I subtract 14 root 2's, how many root 2's do I have? So those are my like terms. The root 2's are all like terms. These are all like terms here. Not this one. This would be like your 2x plus 7x minus 5y, right? Not like term. So I'm just taking the root 2's. I don't change the root 2's, they're going to stay root 2's. So again, I have 20 root 2's, I had 28 root 2's, I subtract 14 root 2's. How many root 2's have I got? I've got 34 of them. So this is 34 root 2. And then my this one here, this last one here, minus 5 root 7, I couldn't do anything with that, and there's no like terms to add or subtract with it. So that's my answer there. These are exact values. When you write the square root of 2, that is an exact number. But if you put it in your calculator, you're going to get a number with some decimals after it. That would be approximate, not exact. Whenever your question says exact, that means you do not start getting out your calculator and rounding. Some students think it means exact if you write down a whole bunch of decimal places, right? If I said, what's the exact value of pi? And you said it's 3.14159, you wrote out a whole bunch of decimals. That's not exactly pi. This is just pi, right? No scientist even can write pi down exactly to the last decimal place. So there's no way in grade 11 we can. Exact does not mean you're rounding. That is not exact. So now let's go to example 3 because we finished example 2. Example 3 says simplify, so it's the same instruction, but we've got different math. I'm just going to start over here because I would crowd into my red answer there if I didn't. First of all, the power of 2 means write it out twice. That's what it means. If you have a hard time remembering that, you've got to memorize it. That's what it means. It means write it out twice. It doesn't mean throw the 2 backwards into the brackets. No, it never, ever, ever has meant that. And if that's what you thought from elementary school, you're wrong. It means write it out twice. So let's write it out twice. And if it was a power of 4, I'd be writing this out 4 times. 5 root 2, write it out twice. Okay, now, I haven't had this problem before. This is binomial expansion, but these are weird looking binomials here. So first, I'm going to take the first term. This 3 root 3 is my first term, and I'm going to multiply it by the first term over here, which is a 3 root 3. What is 3 root 3 times 3 root 3? So we do integers with integers, radicals with radicals. So I'm going to do this first 3 times this 3. That's going to give me a 9. And now I multiply root 3 times root 3. And it doesn't matter if you have like or unlike radicals, you can still multiply them together. Just like I could take 3x and multiply it by 2y, and I would get 6xy. So I can multiply anything together. So root 3 times root 3 is root 9, which we'll simplify for us later. 9 root 9. Now, we're going to take that same first term, 3 root 3, but this time I'm going to multiply it to the next part of the binomial, which is negative 5 root 2. So 3 root 3 times negative 5 root 2, it's going to be a negative. Integers first, so that's the 3 times the negative 5. The 3 times the negative 5, we do that first, and that's a 15. Then the radicals, so root 3 times a root 2. Radicals times radicals, what's root 3 times root 2? It's root 6. Next, we're going to go to the other terms. Let me switch colors here. So now I need to take this negative 5 root 2, and it needs to get multiplied into both parts of this bracket. What do we get when we multiply the first parts there? So I'm going to get negative 5 root 2 times 3 root 3. Integers times integers. Negative 5 times 3 is going to be 15, negative 15. Root 2 times root 3 is going to be root 6. So that's another negative, or subtract 15 root 6. And then their last term is negative 5 root 2 times negative 5 root 2. Negative 5 times negative 5 is 25. Integers times integers, and radicals times radicals. We can simplify some of this stuff. This is a 3 here. These two are like terms. Negative 15 root 6 minus 15 root 6 is going to give us negative 30 root 6. And square root of 4 reduces to 2. 25 times 2. So we have 27 minus 30 root 6 plus 50. And we have constants we can collect here. 27 and 50 give us 77 minus 30 root 6. Is there any further reducing we can do here, that root 6? No. So that means it's simplified. We've got the radical down as low as we can get it, and we've multiplied all our combinations of everything there. So that question is done. This is our last slide. For correct form in mathematics, we never have a radical in the denominator, like you see in the example below. To rationalize the denominator, we need to multiply the denominator by its conjugate. Okay, let's get back this up here. Rationalize the denominator. The square root of 2 is an irrational number. It's like pi. It's a real number. It's part of all the number system. We know the real number system, but it's irrational, which means it's non-terminating, non-repeating decimal. So the square root of 2 is irrational, and we're not allowed to have a radical in the denominator or an irrational term. So what we have to do is get rid of it. So how do I get rid of 2? Square root of 2. Well, I'm going to multiply by 1. So I'm going to just multiply by 1. Great trick in math that we use all the time, but I'm going to make my 1 look useful. So my 1 is going to be root 2 over root 2. So that's just multiplying by 1, which is completely legitimate. Looking at the numerator, I have an integer times a radical, so they just kind of get pushed together because I can't put the integer into the radical. Now the denominator is root 2 times root 2. What's that? Well, root 2 times root 2 is root 4, which is 2. So we got rid of the radical in the denominator, and radicals are irrational. So we have rationalized the denominator, because we no longer have a radical there. Next one's harder. It's not as easy as the previous one. I can't just say, oh, I'm just going to multiply by root 7 over root 7, because that worked last time, right? Root 7. Because imagine if I did that, I'd have to multiply both of these terms by root 7. Then I'd end up with a 4 root 7, so that's not going to work. So I can't do that. When we have a binomial, we have to multiply again by 1 to rationalize, but our binomial has to be whatever the opposite sign was. So this happened to be a positive, I'm going to put a negative there. Just the opposite. It's not always a negative, it's always the opposite sign. So the opposite sign goes in there, and you will see why this works in a second. Looking at the, switch colors, looking at the numerator, we're going to get 1 times all that purple stuff, which is just going to be all that purple stuff, right? That's just 4 minus root 7. How about the denominator? These are actually binomials now. This is going to be like our previous example. We're going to have to do 4 times 4. That's a 16. 4 times negative root 7 is negative 4 root 7. Root 7 times 4 is plus. The integer goes first. Trumps the radical. These lines should always go over your whole thing. And then root 7 times negative root 7 is negative. Oops. Yep, negative root 49. So that looks worse. Doesn't that denominator look worse than what we had before? How can that possibly be helping us? Well, maybe you've noticed that we have a minus 4 root 7 and a plus 4 root 7. So those are going to cancel each other out. That's why we needed opposite signs here. One positive, one negative, so we'd get a negative one and a positive one. Those are gone. Square root of 49, of course, we know what that is. So we're not going to have any radicals left in our denominator. We have 4 minus root 7 in the numerator. I can have a radical there, that's no problem. These two are gone. So I have 16 minus 7. 16 minus 7 is 9. So I get 4 minus root 7 over 9. And now I have a denominator that is rational. I've rationalized my denominator again. These are operations with radicals that we need when we're working with quadratics. One of the big reasons is because of the quadratic formula. The quadratic formula, as you know, has that whole negative b plus or minus the square root of b squared minus 4ac, right? That whole radical in there. And we're not just going to get out our calculators all the time to figure this out. We're going to have to work with radicals. So this is good practice right here. So that is our final piece that we needed to do to work with radicals.